So
Cauchy Riemman condition.
Yeah. So are these functions entire?
Entire, it was analytic, right? Everywhere.
Analytic everywhere.
Yeah, give me a second. Open. So not. So I need to remind myself, I don't, everything is mixing in my head. Analyticity, it should be, the function should exist and it should be exist at the function z naught, right?
Yep.
So are the function e powered by z entire. The point z is a point in the complex z plane. Shows that cosinus z equals cosinus z. What's the cosh y?
Hyperbolic cosine.
Hyperbolic cosine, right. How you can remember everything? I mean, like it's trigonometry.
I try.
Yes, I have.
Okay, so so we want to check if this is entire. Remember the Cauchy Riemman conditions? du dx
u over dx equal d something. I mean, like we need to find its derivative.
Equals dv dy.
Equals dv dy.
And then du
dy.
dy equals negative.
Equals dv
dx.
Yes.
Yeah. Can you confirm that these are the Cauchy Riemman equations first before we
move on?
Yeah, I don't think I trust my memory, but maybe I can also confirm from my end.
Yeah, give me a sec to do very quick. Derivatives. Let's composition continue. Oh, sorry. Oh,
bless you. Yeah, they're okay. Yeah, they're good.
du dx equals dv dy, and du dy equals negative dv dx, right?
Yeah. So this is going to be
ex gonna be the same, ez.
So ez is going to be ex plus iy, right?
Yes, right. Yes.
So
yes.
if you do a d, so it's going to be ex.
Just ex. dv dy, du dx will be just ex.
So we have to bring in the, first of all, the u, you have to write the function as u plus iv.
Yes.
You see this is not in that form. It's not in the form u plus iv.
But u, it's real numbers, and v, it's
But you see,
imaginary.
this is a power. You cannot say that U is that and V is
Oh,
that. No. So you have to bring in
okay.
Euler's formula. So it's going to be
Cosinus theta?
EX multiplied
equal,
by EIY, right?
yes, EIY.
So this is EX, and then EIY could be cos
Cosinus
Y
theta y
plus
plus
I sine
sine y.
Y. And so now you could say E cos Y, I mean EX cos Y plus
EX cos y plus
EX sine Y.
sin.
And so now this can be your U of XY, and this can be your V of
V.
XY. And then now we can now do du dx.
Du
So,
dx, it
yeah.
will be, first of all, it will be EX cosinus y.
Yeah, it's going to be
plus
EX.
Plus EX times negative sine y.
No, remember U is the real part of the function. And
yes.
Also it's with respect to X. So the cosinus.
Oh, cosinus y we don't touch.
Yeah,
Right,
the
right,
cos
right,
Y
right.
is going to be just a constant.
Yes, the same. Yes. It will be just EX cosinus y.
And then we do
okay,
dv dy.
dv dy will be
EX
E
cos Y.
X times cos y, right?
And they are equal.
Yes, and
now we do
it's
u dy.
du dy will be EX times negative sine y.
So negative EX sine Y. And then we do dv
And
dx.
then dv dx will be
So negative dv dx.
just EX. Yes, negative, it's minus.
Yeah, so it's going to be negative EX sine Y. So
yes,
again, you can see that these two are equal, right?
Mm-hmm.
And so EZ is entire.
Okay, EZ is entire.
Yeah.
Okay, second one, B, it's cosinus Z. So it's, we can say that cos
Oh, we
X
have
plus
1 over Z.
IY.
We have
Oh,
1 over Z in there somewhere.
Yeah, let's do it 1 over Z.
Yeah.
So 1 over Z is entire or not. It will be 1 over X plus IY. And we can divide it to two parts, 1 over X plus 1 over IY.
No.
No?
No.
We can tell it, we can write it right like this.
No, we can't. You see, it's the same thing. Look at 1/3 plus 1/5. You know, is it the same as 1 over?
No, of course not.
No, it's not. It's not the same as 1 over n.
Yeah, so we can say that.
So I think the best thing is to multiply by the complex conjugate.
X minus IY.
Yeah, top and bottom by X minus IY.
So 1X plus IY times X minus IY in the numerator and in the denominator, X minus IY. It will be X minus IY in numerator and X square plus no. Y square, right?
Yeah.
There's no plus Y square. IY X and negative IY X will cancel out. So now we can say that x over x squared plus y squared, it's a real part, and minus iy over x squared plus y squared, it's a imaginary part. Or we can say yes, plus I minus y. So now we can do our du dx. Du dx, it will be, okay, got it. It's one, it's, we can say it 1 times x squared plus y squared minus x times 2x divided by x2 plus y2 squared, right? Am I right?
Let's see. So this is going to be x squared plus y squared negative 1 plus x, and then this is negative 1 x squared plus y squared negative 2 multiplied by 2x. So this will actually be 1 over x squared plus y squared. And then this is going to be minus 2x squared over x squared plus y squared. This is squared.
Yes, right.
Which we could also write as you could do x squared plus y squared. So that would be negative x squared plus y squared
x squared plus x squared. Oh yeah, minus 2x
plus y squared. So I just combined them somehow.
Yes, of course. We use different methods.
Yeah.
But the answer is the same. So now we need to find dv dx, dv dy, sorry.
Yeah, dv dy.
Yes, dv dy in this case will be, so my I minus y divided by x squared plus y squared.
Seems like it's gonna be the same thing.
Yes, give me a sec. So it will be minus 1 times x squared plus y squared minus negative y x squared. No, we don't need to use x squared. Times 2y x squared plus y squared powered by 2. It will be minus x squared plus y squared divided, yes, it's the same. So here we can say that it's analytic. And another one, what we need to find, it's du dy. Du dy, it's du dy. And again, x times 2y. Which one are you doing?
I'm doing dv dy.
dv dy, it's the same, they're equals.
Okay.
Negative x squared plus y squared over x squared plus y squared and powered by 2. I mean, okay.
They are not equal. They are not.
Why is there not?
Because if you compare This was
But
our du dx.
mhm.
That was our du
No,
dx. And
it
this is
should
our
be.
dv dy.
No. Hold on. Du dx. Du dx, it's 1 times x squared plus y squared. Negative, yes, minus x, we leave x times 2x. What will be negative 2x squared plus x squared, it will be negative x squared plus y squared divided x squared plus y squared 2. But it's the same, no? You need to, it's not x plus y squared, it's x squared plus y squared.
Yeah.
And
but
you
still
need
it's
to,
not the same.
it will be minus x squared plus y squared plus 2y squared.
Okay.
Do you see?
Oh, where else should I change here? Okay, I've seen the x squared plus y squared.
Y squared, you need to put in denominator on the left side. Minus 1 times x squared plus y squared. You need to make the same denominator.
Okay. X squared plus y squared squared. And then this becomes x squared plus y squared.
Minus negative, don't
and
forget about
it's
it.
negative. So negative x squared minus y squared.
Yes.
So that becomes y squared.
Y squared negative x squared minus x squared. It's the same.
So it's the same there.
Yes.
So dv dx
dv dy.
equals
du dx equals dv dy.
Yeah, so the first condition is satisfied.
Yes. And now we need to check second conditions, du dy. Du dy. So it's x over x squared plus y squared. We can say that.
So I think du dy, if let me try to cheat. Du dy is going to be equal to negative y squared plus x squared divided by x squared plus y squared squared.
dv dy. Oh,
Yeah.
du dy.
Du dy.
I'm not sure. I'm thinking.
You know, it's going to follow the same process the way it did with x, but now you just replace x with y. So in the answer, I just swapped the x and the y.
Maybe.
Yeah. And then if I try to do the same trick on.
I don't think that it will be du dy.
Okay, can you just work it out using the whole process and then you can give me the final answer.
Give me a sec.
Yeah, maybe it could. Okay, yeah. I see. We need to do it all over again.
Yes, because it doesn't work in this case. So we have x, our u part is x over x squared plus y squared. And when we take derivative by y, it will be, we don't need x, it's going to be 0, and x squared is going to be 0.
So it's going to be x.
Only 2y.
X squared plus y squared.
Yes, negative powered by -1.
Divided by -2, and this is a negative, and this is 2y.
Why it's -2?
Because I found its derivative.
Okay, yes. Yes.
So it's going to be -2xy over x squared plus y squared. And that is your dv dy. du dy.
But you don't forget about the square or in the denominator.
Yeah.
Mhm. So, and dv dx will be negative dv dx. It will be positive y divided by x squared plus y squared.
X squared plus y squared multiplied by 2x, and this is -2. It's going to be 2xy. So that condition is satisfied, the second one.
2xy over x squared plus y squared. So, yes, they're equal. So it's entire. 1 over z is entire.
Yeah.
Okay.
Cosine z.
Cosine z will be, we can use the formula, the Euler.
No, they have given us the formula to use. They're saying that cos z is going to be given by that.
Okay.
Okay.
Cos x cos hy minus I sine x times sine hy. Okay. We need to remember this formula. So du dx equals minus sine x times to cos hy, and dv dy equals sine x times, so what's the derivative of sine h?
Cos.
What is it?
Cos h.
Cos h?
Yeah.
Okay. So it will be with a negative sign, right? No, it will be positive, right? Cosinus hy. So this,
and by the way, you should write this as positive, and then this should be negative. And so this is going to be sine x. Cos hy negative, so they are equal. Then do du dy.
dv dx. Oh, du dy, yes.
Yeah, du dy.
Yes. Du dy equal cosinus x times minus sin hy, and dv dx, negative dv dx equals negative. It will be positive cosinus x times 2 sine hy. No, they're not equal.
One is the negative of the other. No, wait.
Yeah, and it's turning to, it should be negative. In the top, it's negative, and we're turning cosinus hy to the sinus hy. It should be changed. Negative sign It's a previous equation. Yes,
No,
this one.
no, it's going to remain. The
No,
derivative
cosinus,
of Cauchy is going.
it's negative sign.
We are talking about du dy, right?
Yes.
It's going to be positive. You know, this is cos h. It's not the usual cos.
It's not usual cos.
Yeah, the derivative
Okay.
of cos h is just sine h.
What about derivative of sine h? It's a positive cos h.
It's positive cos h. So in this case,
Okay.
they don't play around with the signs.
Okay, okay, okay. So in this case, they're equal.
Yeah.
So, and this function is entire. Cos z is entire.
Yeah.
Okay. It was interesting.
That was easy.
Yes. Only derivatives. Proof that the two Cauchy Riemman conditions become in polar coordinates using
Okay. So
prove that
du
dx
so using z equals r that so x over r equals cos theta, y over r equals that, and r equals that. So we are changing variables. So it's a du dr, the other one it's a dv d theta, and then dv d. Oh, okay. So we know that x over r, so x is going to be equal to r
cos
theta, right?
Yes.
And then dx is going to be equal to
R
is going to be equal to r
minus sin theta.
r
Times to the
minus sin theta,
yeah, but it
d
times.
theta.
R
theta.
times minus sin theta.
Yeah. D theta. Okay. So, and then we know that y
Equals R sin theta.
and so
Where
dy
equals R cos theta dy d theta.
r cos theta d theta. And so
we can
this is going to become du. X is r cos theta. R cos theta. Y is
y sinus theta.
r sin theta. And then dx is
R
negative r negative r
sinus times sinus theta d theta.
sin theta d theta.
And dv xy
r cos theta.
Yeah, it's equals. Oh, no, it's not equal. It's, oh, it's equal.
Okay, let's see, can we divide by, let's divide everything by sine theta. So this is going to become du
R cos theta.
This is r cos theta divided by sine
Yes.
theta is tan theta. And then this is going to be r.
Just
And then this is going to be negative r d theta. And then you can see that tan inverse. So theta equals tan inverse y over x. So this only means that tan theta equals y over x, right? Tan theta equals y over x. So I don't want to come to return the y over x there. R equals dot. Okay, I think we can check this one. So basically, all you need to do in this case is to substitute. But I think we can just, so let me try again. So r tan theta. Okay, let's just check.
How we can check?
The solutions?
Oh, yeah. Yes, of course. Yeah, I thought maybe you have, yeah, we can buy some software. Solution 1, 2.
Oh, this we already did.
Yes. So
they did a dr dx. They got
dr
that.
dx.
Yeah. And then they did a dr dy. They got that. And then that and then that.
We can find tangents.
Oh, where do they stop?
Actually, I lost point. I need to. So they're asking us to prove.
They're asking us to prove that, you see these Cauchy Riemman equations, they're just asking us to show that they can also be written as polar coordinates like this. They can be written like this as polar
So now
coordinates.
we need to change xy to the r theta.
Yeah.
I mean, we need to change the function.
Yeah, we need
And
to
he
change
says, yes,
all
and he
the
says that
variables.
x over r is cosinus cos theta, and y over r is sin theta. R it's a length of x square plus y square. Theta equals tangents minus 1. Tangents it's a cosinus over cos over sin.
Yep.
Then du dx equals du dr times dr dx. dr, what's the dr?
The derivative of the length with respect to x.
Oh, yes. So it will be 2x. Oh, no, it's square. It just x. Yes.
Okay. So du dx.
Why it's cosinus cos theta? Du dr times cosine theta. How it changed it?
How he got cos theta? Because you
Yes.
see x squared plus y squared is r. So,
Oh,
so
x
this
over
is
r.
r,
Yes.
and
Yes.
x over r is cos theta.
Mm-hmm.
And the same thing
Okay.
happens. This becomes sine theta over r.
But why he put again next another r? Ah, there is no square in this case. Mm-hmm.
Yeah. So he started there. So the dr dx is there, and then this is the d theta dx. So this becomes the sine theta over the r. How did you get the sine theta over r?
Because y over r is sine theta. He put minus in front of du d theta.
I see.
And yes.
And then he got that.
Mm-hmm.
And then he wants to show that du dr is given by that dv d theta. Okay, and then similarly, he tries to find dr dx. Where did the dr dx come from? So dr dx.
So dr it's x over square root x squared plus y2. We can see it from the previous equation, which equals cosinus theta. And dr dy it's negative y. Why it's not negative? dr dy. Okay, it can be just y. But
You
why?
know, he's just differentiating this. You just look at this equation. You differentiate. That's how he got this and that.
Okay.
The dr dx and the dr dy.
Mm-hmm. It's understandable. Yeah. But why it's y? It should be 2y or 1.
Which one?
I mean, dr dy. Where is the y over square root x squared plus y2? When we're moving in the denominator, it will be, we don't need x squared, we need to take derivative of square root y2 y square, which will be just y. Oh no, we don't, we were not taking derivatives right now.
Okay.
Never mind, I got it.
All right. So it cancels out.
Yes.
It's not 2i because when the half goes down, and this is x squared plus y squared powered by negative a half. If you multiply by the 2y, the 2's cancel.
Yes. Yes. Now I see.
So after that, he gets that, and then he brings in the tangent equation. Then what does he do? 1 plus tan squared theta d theta dx equals negative y over x squared, which gives us that. Okay.
I think we need to get fresh view on this equation.
I think so too.
Yeah, because it's a little bit, how can I say?
Yeah. Yeah, let's try this one. Show that this function has a removable singularity at z equals I. Can you check your notes and
tell what's this?
Oh yeah, I think I remember what a removable singularity is. Yeah. So
I don't remember, unfortunately. If it's analyticity. If you remember, could you show me? I will find it later because it will take time.
So basically, it's going to have a removable singularity if we can, let's say look at something like this. Look at z minus 2. This is a singularity. Z equals 2 is a singularity, right?
Yes.
And then look at the function c squared. Z squared minus 5z plus 6. You see, this singularity is removable. You know why? Because the polynomial at the top, we could write it as z minus 3.
Yes.
Z minus 2.
Z minus 2.
Z minus 2. That's removable. Z equals 2 is a removable singularity because there is a way we can cancel it out.
Okay,
but now if I had something like z divided by z minus 2, you know, z equals 2 is not a removable singularity because there is no way we can simplify this complex function to eliminate it in
Mhm.
some way.
Mhm.
Yeah.
So in this case, we need to prove, shows that the function z powered by 14 plus 1 over z6 plus 1
Mhm.
has a removable singularity at z equals I.
Yeah.
In our case, removable singularity is I. Yes, it's -1.
Yeah.
We can say that
So
z,
we can just factor this. This is going to be
z powered 8.
powered by 7
Okay, yes.
minus I.
Yes, in square, everything square.
Yeah. Minus I, and then this is z powered by 7 plus I.
Mm-hmm.
And then we could also factor down here. We could get z powered by
6.
3 plus I,
z3 minus I.
z powered by 3 minus I.
We can make, we can multiply to the denominator. Z squared plus 1 times z squared minus 1 minus, oh no,
It's
1.
going to take us back to where we came from. Okay, let's use a hint. Note that the numerator and the denominator are analytic functions and both go to 0 at z equals I. Use L'Hopital's rule to find that limit by taking derivatives of the numerator and the denominator with respect to z, and then taking the limit, show that this limit exists. So basically, if you want to show that z equals I is a removable singularity, you just compute the limit. So you just need to do the limit z tends to I, z powered by 14 plus 1 divided by z powered by 6 plus 1. And using L'Hopital's rule. What?
No, if we are not using L'Hopital's rule, it's this limit is gonna fail because z power 6 is -1.
Yes, and because it fails, you have to use L'Hopital's rule. So you are trying to remove that failure.
Mm-hmm.
So this is going to be 14 z13 plus. So 14 z13, the one is going to vanish.
Yes, for 14,
and then this is going to be 6
z5.
z5. And then this is, if you simplify, it's going to be limit z tends to I, 14z to the power of 8.
Yes.
And then 6. And so this is going to be 7z8, 3. And then this becomes -7/3. So the limit exists. And so the point z equals I is a removable singularity. Yeah.
It was not so difficult. It was tricky.
Yeah.
We didn't think about L'Hopital's rule.
Yeah. So basically, if you want to define a removable singularity, you can just say, if the limit of the function can be found at that point, then the point is a removable singularity.
Okay.
Yeah. Okay, number 4, write z in polar coordinates and show that the function 1/Zn is differentiable at all points in the plane except at z equals 0. for n greater than or equal to 1 by using problem 2 above, clearly when z equals 0, the function blows up. Therefore, it is not analytic at z equals 0. What is the order of the pole at z equals 0? So basically, if a question is asking you to show that a function is differentiable, it's the same as asking you if it's analytic.
Yes.
So you just need to do Cauchy Riemman equations.
Okay. Du dx. So we need to find. So we have a function 1 over z powered by n. We can write it as 1 over x plus iy powered by n.
Maybe you could just find its derivative, because let's see, I could just do z power negative n. We are doing a d. I could just do a d dz on it.
Negative n.
Negative n z.
Z n minus 1.
Z.
Minus 1. Negative 1 minus 1.
Negative n minus 1, right?
Yes.
Which is equals to negative n over z,
square z
n plus 1. So the derivative exists at all points apart from z equals 0. So we just found the derivative.
Yes,
it's
and
there.
We don't need to find dx dy and compare them.
Yeah, that's going to be complicated. When I saw that. Oh, and by the way, you did calculus in your university.
Yes.
Right? I just realized that in calculus 1, for real valued functions, we just used different terminologies. You see, for limits, actually, a removable limit in calculus 1 is now being called a removable singularity. And then a differentiable function in calculus 1, in complex analysis, it's being called an analytic function. So it's the same thing. Basically, they're just playing with words. Let's see. I'm just interested to see how they did. Oh, they got 7/3 like us for problem 3. They got the limit.
And 4.
And then 4, what did they want us to do in 4? Wait, which?
Yeah, here's the solution. He's dividing Rn times E. Oh, he's using problem 2 above.
Yeah, he's using Cauchy Riemman equations. He's using Cauchy Riemman equations, and
I still have some gaps in poles. I don't understand when he's saying so. Limit of z and f of z approach 0. So it equals 1. In our case, it does not equal 1. It just equal -1 over z n plus 1, which is not 0.
You see, whatever we did was not the limit. We just did the derivative.
Oh yes, we just did the derivative. But how we can find poles from derivatives? We can't, right?
You see, a pole, you can never find the limit of the function when z is approaching the pole. Yeah. So in short, he's just, remember this definition for poles? Remember we said that a function fz has a pole at z equals k if we can do the limit. It has a pole of order n. It has a pole of order n at z equals k if the limit as z approaches that pole k, and then you do z powered by n multiplied by that function f of z equals some constant c. That was the definition of pole, a pole of order n. It's defined like that. Yeah. And so here, to find out if the function has poles, he did limit as z tends to 0. He wanted to check whether 0 is a pole. And then he did z powered by n. And then the function was 1 over z to the n, right? So did he get a constant? Yes, he got a constant. And so the function has a pole of order n at z equals 0. Yeah.
Poles of order n at z
Equals
got
0.
it.
So for number 4, he didn't want us to use the simple method that we used. We are going to revisit this method with a fresh set of brains. Show that this function is differentiable.
Which one? 5, 6? We're looking for 6.
6. I think we already did 5. Oh,
no.
Okay. Show that this function has poles.
Where is the pole located? Find the order of each of the poles. Observe that the singularities at these poles are isolated. There is a sigma neighborhood.
So we want to show that this function has poles, right? So let's do limit
of z square
of z tends to
0.
-1.
Why -1?
Z
Because
plus 1 squared. So I'm seeing a pole at -1 because of the z plus 1. And then f of z, it's going to be equal to, this is going to cancel, right?
Cancel out.
And then we plug in -1, so that's going to be 1 over, this is 1 plus 4, 5. And then this is
times
1.
1 plus 2 plus 2, 5.
1 plus 2, 3, minus 2. 3 minus 2, 1. So it's going to be 1 over 5. So we found the limit as z was approaching -1, z plus 1 squared f of z. We got a constant, and so we have a pole of order 2.
Order 2. Why 2? Oh yes, of order 2, right?
Because -1.
Because it's powered by 2, right?
It's powered by 2.
Of order 2 at z equals -1. But he's asking also to check it for isolations, right?
Yeah.
Oh, no, it's not. Sorry, no, we don't need to check. We need just to find. So we can, now we're trying to find another limit where z approach -4.
No.
No?
So z is going to be approaching.
It can approaches 2.
2i. Because you see, this can be written as z plus 2i multiplied by z minus 2i. So if you follow the same process, you're going to get 2i is a simple pole. That's a pole of order 1, right? Negative 2i again is a simple pole of order 1 again. So far we got 3 poles. Negative 1, z equals negative 1 is a pole of order 2. Z equals 2i is a simple pole. Z equals negative 2i is also a simple pole. Yeah.
And also we need to x, it will be x plus 2 times 2x plus 1. No, it will be 3z. Z plus
so let's, oh, you're looking for a pole here in that one?
Yes, yes.
So there we could use a quadratic formula. Z equals negative 2 plus or minus the square root of 4
minus 4ac minus 4. Determinant equals 0.
No, it's going to be 4 minus 8. It's negative 4.
4ac, yes.
Divided by
4.
2. So this is going to be negative 2 plus or minus
2 square root I.
2i divided by 2. So the other pole is going to be negative 1 plus I. This will be a pole of order 1. And then negative 1 minus I will be another pole of order 1.
Okay, yes, I see. Got it.
So negative 2i, positive 2i, negative 1, and then negative 1 plus minus 2i. Those will be the simple poles.
Did he do, where's the negative 1 just?
What?
Could you open solutions? Where is the negative, where is the approach negative 1? Oh, it's right here somewhere.
Yeah,
I see it.
It's there. Yeah, all of them are there.
Okay.
Show that the function, this function is differentiable or has a derivative only at z equals 0.
So we need to understand, is this function analytic or not? Let's read now. Please read this. Since the function does not have a derivative at any point in the z-plane except z equals 0, it's not analytic at every point in the z-plane except possibly at z equal where it doesn't did have a derivative. So we next investigate if the function is analytic at z equals 0. But first of all, we need to understand, does this function analytic or not? And we can find it by Cauchy Riemman condition.
As far as there is a z bar in the function, it's not analytic.
Okay. If we have z bar in the function, it's not analytic, right?
Yeah.
Even if we can cancel it out. For example, just in case, I mean.
Okay, just to be safe, let me say in many cases. Because if you bring up other cases, maybe it can be forced to be analytic. But whenever out of experience, I've never seen an analytic function that has got a conjugate in it. Yeah. Okay, I believe this is going to be a long explanation. Oh, I knew it. So they did check the CR conditions. So let's see. I told you it's not analytic, right?
Yes.
Let's see what the CR conditions said.
What's the second CR condition? Oh, okay. I understand. Sorry, I thought maybe there is something.
Oh,
new that I don't-
CR condition, Cauchy Riemman.
It's Cauchy Riemman condition. Yeah. No, I was wondering about second. I understand. Never mind.
Yeah.
Second rule. Yes.
So where did they make the conclusion?
At the end, this function is nowhere analytic in the z-plane.
Yeah, so it wasn't analytic.
Mm-hmm.
So they shown it's not analytic using z bar. And then here they are trying to talk about the neighborhoods to show that the point z equals 0 is an isolated singularity.
Mm-hmm.
Yeah. Okay. So we are going to review this definitely.
We're okay with limits.
We did that. We did this, but we
Oh.
are going to review their method. We did that with the L'Hopital's rule.
And we need to review the second.
Yeah, we need to review this one.
Fourth and sixth.
Yeah.
Second, half.
Yeah, 50%. Yeah.
This is what I exactly scored in the last exam.
Yeah.
Okay.
Yeah,
so,
but it's just a review.
Yeah. I actually didn't understand how. So, about our future work, you said it's better for you to send money by PayPal, but do you have WISE, WISE application?
Which one? WISE? No.
Yes. No.
No.
Okay. I need to figure out with my PayPal.
Yeah, you can just yeah.
Okay, send me all from. I mean, like, how is there any number or a mail where I should send?
Mail.
Because I forget. Yes, I forget how to PayPal works.
Yeah.
And can I just schedule with you with WhatsApp before I figure out how the Google Calendar works?
Yeah.
Yeah. Okay.
So if you schedule with me on WhatsApp, I will schedule with you on calendar. I'll just make it official on calendar.
Okay. Cool.
Yeah.
Sounds great.
Yeah.
So okay, I got your mail.
Yeah.
So Steven, that's it.
Yeah.
It's your time for rest. Take a rest. Yeah. I understand you're tired for teaching whole day.
Yeah.
Okay. I'm not gonna take your time. So see ya.
All right.
Okay. Bye.
Bye-bye.